welcome to another GCSE Computer Science video on data representation with me, Mr Goff, from mrgoff.com. Today's video will focus on storage units and binary. The smallest unit of storage is the bit. A bit can store a single digit that is either a 0 or a 1. A byte is a group of 8 bits, and a half a byte is known as a nibble. You are probably already familiar with some of the decimal prefix terms used to describe the amount of storage a computer has. Terms like kilobyte, which is 1,000 bits, megabyte, which is 1,000 kilobytes, and gigabyte, which is 1,000 megabytes. These values are based on powers of 10, with each being 1,000 times larger than the last. The pattern continues on from gigabytes to terabytes and petabytes. After this would come exabytes, zettabytes, and yottabytes. In the early days of computing, these prefixes were also wrongly used to describe binary values. The binary prefixes kibibyte, mebibyte, and gibibyte are now used to refer to these same terms. As you can see, the values are not identical. A kilobyte is 24 bits less than a kibibyte. By the time we get up to megabytes, the difference is about 48.5 kilobytes. When we get to a gigabyte, we'll find that we're getting about 74 megabytes less than we would expect to get from a gibibyte. This pattern continues with the gap widening as we move on to look at tabibytes and pebibytes. If we were to look at bigger storage units in the binary prefix, they would be exbibytes, zebibytes, and yobibytes. It is a strange quirk of computing that when they advertise storage spaces, they use the decimal prefixes, but when you go onto the computer to see how much storage you actually have, they use the binary prefixes. This has led many people to thinking that their hard drives are not as large as what they paid for. To help us understand binary, it's best to take a look at what we know and understand about our current counting system, Denary, also known as decimal. This is a base 10 system. It's called base 10 because there are 10 possible digits that you could put in any given column, the numbers from 0 to 9. If we want to express a number greater than 9, we need a new column to record how many tens we have. This gives us the opportunity to record up to 9 tens and 9 ones. However, if we wanted to record how many hundreds we have, we need another column again. Now let's take a look at binary. Binary is a base 2 system because there are only 2 possible digits, 0 or 1, that you can put in any given column. So we can either have no ones or we can have 1 1. If we wanted to store 2 in binary, we'd need a second column that can record the number of 2's we have in our number. This allows us to make a largest number of 1 1, which would be 1 in the 2's, 1 in the 1's, a value of 3. If we wanted to make a 4, we would need another column. This pattern continues. Therefore, you can see that the column headings in binary start at 1 on the right and they double as we move across as we go left. This pattern also means I know if I have a 1, meaning I've got one of each of the column headings to the right of 128, I know that I've got 1 less than 128, or 0, 1, 1, 1, 1, 1, 1, 1 in binary represents 127. There is a formula you can use to calculate the largest binary number you can make with any given number of bits. That formula is 2 to the power of n minus 1, where n is the number of bits used to make the number. This is not to be confused with the number of different combinations you can make with n bits, which is always one larger because one of the combinations represents the value 0. To convert a number from binary to denary, start by writing out your binary table with all the column headings at the top as they should be, starting from 1 on the right and doubling as you move left. Write your binary number below with the rightmost digit of your binary number in the ones column. All that remains to do is add up the column headings where our binary number has a 1 in the column. So this number, 1101001, contains 164, 132, 18, and 11 for a total of 105. There is also a short algorithm you can follow to convert from denary to binary. First, write out an empty table with the column headings for binary. I'll convert the number 74 to binary to show you how it works. Step 1. Starting on the left, find the first column heading that is not larger than our number. Place a 1 in that column and a 0 in any columns that you have passed. In this case, we place a 1 in the 64's column. Next, subtract the column heading where you placed a number from the number we are converting. We were converting 74. If we take away 64, we have 10 left to use. If the new number is not 0, then return to step 1. If it is 0, then you've already finished. You can fill in with zeros the rest of the number. We go back to step 1 with our new number 10, and starting on the left, the first column heading that is not larger than our number is 8. So we place a 1 in there. We place zeros in the columns that we've passed. We take 8 away from 10. Our new number is 2. We start on the left for the next column heading we haven't looked at, and 2 is the biggest column heading that we can see. We place a 1 in there, we subtract it, and we have a value of 0, so we know we can complete our number by filling it out with zeros. There is also a second method you can use to convert from denary or decimal to binary. This method is called the divide by 2 method. With this method, you repeatedly divide the number by 2 and record the remainder you would get by doing so. Then you read from the bottom to the top to reveal the number. If you look below as we convert the number 74 again, you can see that 74 divide 2 would be 37 with no remainder. 37 divide 2 would be 18 with a remainder of 1. 18 divide 2 would be 9 with a remainder of 0. And we carry on with this pattern. One of the things I don't like about this method is that students often forget that we're going to read from the bottom to the top, so the final number you get will always be a 1, and students sometimes forget to divide 1 by 2 and come up with that remainder of 1. That's always going to be the last step when you use the divide by 2 method. Other concerns I have with this method are students regularly forget to then read from the bottom to the top. That is, the number is 1001010, not 0101001, which would be a completely incorrect number. This method generates a binary number that is as many bits long as it needs to be. If you need it to be, say for instance, 8-bit, you would have to add the leading zeros yourself. With that said, if you are confident you can avoid the pitfalls of this method, and you prefer it to the other method, you are still quite welcome to do it this way. It will result in the correct answer. That brings us to the end of our look at storage units and binary. I've been Mr Goff for mrgoff.com. I hope you'll join me again for another video on data representation, this time focused on hexadecimal. Bye for now.